The Dynamic Learning Maps Alternate Assessment System is a new assessment designed to more validly measure what students with significant cognitive disabilities know and can do. This presentation on functions and rates will provide information to teachers of students with significant cognitive disabilities who will complete the alternate assessment. This presentation is one in a series that supports teachers of students with significant cognitive disabilities in their efforts to teach and assess. Sponsored by a grant from the U.S. Department of Education, Office of Special Education Programs, this training is part of the professional development efforts of the Dynamic Learning Maps Alternate Assessment Consortium. Functions doesn't actually appear in the essential elements until 8th grade. But in order to help students understand functions when they become a part of the essential elements, we need to teach a number of earlier developing understandings that we can build upon when introducing them. A good place to start is with counting. In the module on forms of number, we discuss the idea that students have to learn what to count and how to count. We also discuss the actual forms of number: concrete, pictorial, and symbolic. Recall that symbolic forms of number include numerals and mathematical symbols such as the equal sign and the addition sign. We want students to experience all three forms of number throughout their instructional experiences. In other words, if the student is counting using concrete materials, 1, 2, 3, the teacher will model the pictorial, 1, 2, 3. And the symbolic representations, 1, 2, 3. And as the student gains understanding, we want them to also use the pictorial and symbolic representations. Building these understandings early will help students as we begin to introduce functions in the upper grades. In learning what to count, students have developed strategies from remembering what has or has not been counted. Students may organize their manipulatives using tools that help them keep track of what they have or have not counted. For example, this image shows two mats. Students can use the mats to organize the objects while they count. They can move the objects from one mat to the other as they pair each object with one and only one number, and each name with only one object. An abacus is another tool students can use to organize their counting. Students move a specific number of beads across the string as they are counted. These are simple examples of ways that students can learn to organize concrete materials when counting. As students begin to think about functions, they go beyond simple counting. The goal of functional thinking is not just learning to count, but learning to count quantities that are related to each other and recording the relationship in a structured manner. For example, suppose you want to describe the total number of eyes that 5 people have. Students could simply count the number of eyes, but this would not represent a relationship. They need to count both the number of people and the number of eyes. So 1 person, 2 eyes, 2 people, 4 eyes, 3 people, 6 eyes, and so on. Functional thinking requires students to keep up with a lot of numbers. As a result, we need to give the students a tool to help them keep up with the information. A function table can serve this purpose. At first, teachers model how to use the table to record information showing the students the relationship between the two quantities. Teachers will want to help students attend to where the numbers go on the table and the meanings represented in the position of the numbers. Gradually, the student needs to take on the responsibility of keeping track of their counting and begin to recognize when and how to use this table to organize data. The process helps students visually and/or tactually and cognitively look across columns and keep track of two quantities simultaneously. Once students understand how to record their data, They are able to shift their focus more closely on the relationships in the data. Change is an important mathematical idea that can be studied using various tools. Here, students use the function table to help organize the data, to help them analyze the change from one row to the next, or between extensions. Teachers could guide students to compare the differences within and across the columns. In this case, the number of people increases by 1, while the number of eyes increases by 2. So let's stop here for a moment and define exactly what a function is. It is a mathematical statement that describes how two or more quantities vary in relationship to each other. And although there are many types of relationships between quantities, functions are special because the value of one quantity is uniquely related to the value of the second quantity. As in our example, the number of people directly corresponds to the number of eyes. Pause for activity 1. Prior to the activity, we began to discuss the need for students to focus on the relationship within the data. But in order to do this, students need to have had some experience with patterns, because these relationships within data are patterns. Please see the module on patterns and sequences for a more in-depth discussion on patterns and teaching patterns. Here we want to look at growing patterns by a specific quantity. Your screen shows an example of a shape that we are going to grow in a geometric pattern. Students can build on their understanding of simple patterns by creating extensions of shapes like this in a logical manner. Building the patterns with physical objects such as tiles, counters, and blocks allows students to experience the growing pattern and make changes if needed. Take a moment and determine the quantity by which the pattern grows. The pattern grows by 3. As students create each extension in the growing pattern, they can record their findings on a function table or on a graph. Notice that in order to make the geometric growing pattern an example of functions, we actually created 3 different shapes and recorded the data. If students were to just extend the same shape over and over again, they would be modeling a growing pattern, but not necessarily a function problem. What makes it a function problem is when we model and keep track of how two quantities vary in relationship to each other. When analyzing a pattern, students should try and determine how each extension in the pattern differs from the preceding extension. Instructional examples can focus on students using counting, additive, and possibly even multiplicative strategies to determine the growing pattern. Students will start by looking at the data and reasoning about the numerical relationships. In other words, finding the rate of change, and then extend the pattern to a larger unknown quantity. For example, how many parts would you have if you had 7 shapes? So clearly, figuring out the change within and across a function table is important. The same change within and across numbers can be found between the x and y axis on a graph. We call this the rate of change, or the rate that describes how one quantity changes in relation to another quantity. Observing the numbers that are paired up and determining the rule for the input and the output find the rate of change. If we say every dog has 2 bones, then we could use the rule, or the rate of change, dogs times 2 equals bones, to figure out how many bones we have for any number of dogs. Let's look at another problem so we can think about rate of change a little more. The problem on your screen: if Sam can mow 1 lawn in 2 hours, how many lawns can he mow in 8 hours? Can be simplified by creating a visual or tactual representation. We can guide our students to think about the unit rate within the problem, in this case, hours. And we can help students use representations or drawings to solve the problem. Sam can mow one lawn in 2 hours. So let's create a pictorial representation. One lawn in 2 hours. And a written expression, one lawn equals 2 hours. The problem then asks us, how many lawns can he mow in 8 hours? Guide students to count out 8 clocks in groups of 2, just like at the beginning of the problem, so they can see the relationship or rate of change is 2 hours for every 1 lawn. The function table would look like this. The rate of change is that for every yard that is mowed, the number of hours will increase by 2. We can also graph the inputs and outputs of the function, showing the rate of change in a different format. 1 lawn every 2 hours. In the essential elements, students are asked to interpret this type of graph as increasing, decreasing, or staying constant. As the number of lawns increases, so do the number of hours. Pause for Activity 2. As students gain understanding of rates and functions, we need to help them move from language descriptors such as the number of people and the number of eyes to more mathematical descriptors, where P represents the number of people and E represents the number of eyes. In this way, we are using language descriptors as a foundation for developing mathematical language. The idea that a variable represents a quantity that can take on a range of values is not a simple concept. When students begin to use variables to describe a mathematical relationship, we as teachers need to be explicit in helping them understand that a change in one variable creates a change in the other variable. The types of examples you have seen thus far in the module will help them come to understand the concept. For instance, think back to the problem about the total number of eyes that 5 people have. Because we figured out the pattern or the rate of change in the problem was that each increase in one person was associated with an increase in 2 eyes, we can actually solve the problem for any number of people using the formula. People, or P, times 2 equals the number of eyes, or E. P times 2 equals E. When students examine real-world functions, the input and output data can be represented in multiple ways using words, pictures, and numbers that can be organized on charts or graphs or represented by equations. The students then determine the relationship or rate of change by observing the numbers that are paired up and determine if the relationship between the numbers increases, decreases, or stays constant. In this example, the student has 3 pairs of pants. Every additional shirt will result in an additional 3 new outfits. 1 shirt with 3 pairs of pants results in 3 outfits. 2 shirts with 3 pairs of pants results in 6 outfits. 3 shirts with 3 pairs of pants results in 9 outfits, and so on. The rate of change given 3 pairs of pants is that the addition of 1 shirt results in the addition of 3 outfits. This concludes the module on functions and rates. For more information on instruction aligned with the DLM essential elements, please go to www.dynamiclearningmaps.org.